Hello everyone, my name is Runze Zhang. Today I will be honored to present our research, identifying incoherent search sessions, search click fraud remediation and the real-world constraints. This work is done in collaboration of Georgia Tech and Microsoft. Search engine has been suffering from the click fraud for a long while. Mostly, search engine earns their profit from their ad network by placing ads within their search result pages. Specifically, while many advertisers seeking for more business opportunities, they will place their ads on search engines. And besides, search engines have a lot of fantastic users who use the search engines and may engage with ad links. Under a pay-per-click business model, when a user clicks on an ad, the advertisers will pay search engines for it. In other words, these users will make purchases from the advertiser's page, resulting in a win-win situation. However, it's not always the case. In fact, there are a few click fraudsters who use the bots or auto scripts to engaging with the search engines. This requires still making clicks on the search engine, resulting in advertiser being charged continuously. However, since the click fraudster never buy anything, the advertiser receives unexpected advertising efforts, losing budget without gaining new business. Furthermore, the search engine suffers from the reputational damage and loses the customers long-termly. This actually motivates the search engine to actively detect and block such traffic. However, this task remains challenging, especially to our fraudulent traffic investigator, Peter. Peter may investigate into different facts from a request. For example, Peter may look into its source IP's reputation, flagging traffic with suspicious request headers, or examine the user account metadata associated with each request to identify the fraudulent requests. Unfortunately, the fraudsters evade these detections by mimicking their traffic patterns of legitimate users. They deploy the proxy to hide their real source IPs, manipulating request content, and create the fake user profiles to make their fraudulent traffic appear from the legitimate users. As a result, for each request, Peter has limited reliable information to evaluate whether it is fraudulent or not. To solve this challenge, this research relies on the insight of the search queries used to generating the search results. In fact, the fraudsters need to send the search query to make the search engine return the ad links, and then they can simulating the ad clicking with their bot or scripts accordingly. And this resulting into the click searches are closely tied to the queries issued by the fraudsters. By taking a closer look into fraudsters generated search queries, in most cases, these requests are randomly generated, which have very limited contextual correlation with each other. In other words, they are illogical searches. In contrast, the search from the general users are likely to remain single thread at a time, and people may add and remove the keywords to refine their search results. For example, a user looking for the hotel in San Francisco may add the budget constraints, or they will bring a pet together. This results in a semantically coherent session. And as a result, Peter can leverage this information to analyzing the search queries and detect the fraudulent traffic. To this end, we present COSAC, an end-to-end framework to automatically flagging incoherent sessions. The COSAC takes the traffic log as the input and starts with the session generation. In detail, COSAC generates individual search requests into session and performs the session slicing based on temporal information. COSAC also derives the statistical matrix for the route from the raw data. Besides, COSAC features a multi-dimensional semantic feature encoder to extract the literal semantic, temporal, and ad-click behavioral features from search sessions. We will cover more details for this part later. Out of the statistical matrix, COSAC is able to derive a ground truth dataset from the real-world traffic logs. With this data, COSAC trained and tested the incoherent index evaluator, which is able to infer whether a search session is fraudulent or not. Taking a closer look into how COSAC collects the features from generated search sessions, let's use just this session as an example. From each request, COSAC first takes the search query and generating the tokens for each keyword with a pre-trained language model. And after that, COSAC performs average pooling to get the query embeddings, which is also considered as a literal semantic feature vector. Besides, COSAC takes the request timestamp as the input and takes both the absolute request time and the intervals between the requests, which is then considered as the temporal feature vector. Last but not least, Cossack takes the ad-click behavior information and extracts the statistical features such as the count of the ads, clicks, and revenues as the ad-click behavior feature vector. As Cossack extracts the 3 different feature vectors for each request, this procedure is populated to all the requests in a session. After that, Cossack's sequence model takes the feature vector from all these requests in sequence and derives the final fraudulent session classification result. Thanks to our collaborator, we are able to harvest the ground truth dataset from Bing.com's daily traffic, resulting in 200,000 of the fraudulent and benign sessions separately. We're using 70% of these for training and 30% for testing, as the breakdown shown in the red table. For benign sessions, we collect them from the long-termly trusted users. And in terms of the fraudulent sessions, we collect those from the 2 different subsets. For traffic can be captured by the predefined filtering rules, we consider this from the naive attackers named naive fraudulent sessions. And besides, we look into the traffic from the mostly abused websites derived from the statistical matrix, name them the target-specific fraudulent sessions. In terms of the results, Cossack achieves an average of 94.17 in accuracy with 95.79 in precision and 92.40 in recall. Driven down into each dataset, towards the fraudulent subsets, Cossack achieves 93.49 and 91.31 accuracy separately. And besides, Cossack makes a 95.53 true negative rate on the benign sessions. This result outperforms our baseline model, as more details documented in the paper. Next, we perform our ablation study to evaluate different features' importance. We train Cossack's prototype with different dataset sizes and features groups. Overall, when the data size is very limited, Cossack's prototype using temporal features itself can set up a good decision boundary. However, when Cossack's model is trained with a larger dataset, using literal features solely achieves the promising performance. There is no doubt like Cossack can benefit from all the feature groups and achieve the best performance. There is definitely much more in the paper. We provide the details about our preliminary investigations of the search coherence, which highly motivated this research. Besides, we present additional evaluation results, including Cossack's drift measurement and base layer comparison. We also show 2 case studies on real-world fraud campaign, highlighting existing evasion approach deployed by those fraudsters. Finally, we would like to thank our collaborator again, Microsoft, and please feel free to reach out to me for any questions. Thanks.